Hello and happy December 3rd. Well, since today is December 3rd, I want to talk about something to do with the number 3, and that is the unitarity triangle. Now, the unitarity triangle is a visual representation of what is known as the Kobayashi-Maskawa matrix, or CKM matrix, and this is what it looks like mathematically. Yeah, it's quite abstract and scary, and that's why we have the unitarity triangle to represent it. Now, this matrix tells us about how the quarks and antiquarks interact, and it tells us why nature seems to favour matter over antimatter. And this is quite a surprising thing, but quite a good thing really. If we didn't have more matter than antimatter, then we'd never have stars and planets, we'd never have anything solid, we'd never have life. So it's a good job that the universe favours matter over antimatter. And this is one of those examples of a broken symmetry I talked about in yesterday's video. I mean, naively, we'd expect nature to say matter, antimatter, it's all the same thing really, I'm going to treat them both the same way. But no, nature seems to favour matter over antimatter. Now, the CKM matrix and the unitarity triangle alone can't explain the whole picture, but they do give us our best insight into why nature says that matter is favoured over antimatter. Now, the unitarity triangle is a way of combining several different measurements into a single triangle. And this triangle really only has 2 degrees of freedom. These are called rho and eta, and we plot these on the complex plane, and this is how we end up with these beautiful diagrams. Now, if the standard model is really the only source of this asymmetry, which we call CP violation, then it should look like a normal triangle like this. It should have a single apex at the top. However, if there's something else going on that the standard model can't describe, then the triangle would look like this. There would be no single apex at the top. These 2 lines wouldn't meet in one place. And what happens then is we end up with probabilities not adding up to 1. And the only way that probabilities can not add up to 1 in the standard model is because there's something beyond the standard model which takes the remaining part into account. Now, the unitarity triangle has been quite precisely measured by experiments such as Barber, Bell, and now LHCb is joining in, making contributions there. And so far, what they've done is made the error band so small that they start to show tension. So where we expect the apex to meet, there's a bit of tension. These are sort of being dragged away from each other. Not enough to be conclusive yet, but enough to be very interesting. And so, for example, we've had results such as B to D tau nu and B to D star tau nu coming out of Barber this year, and they showed a dramatic disagreement with the standard model. And when you combine that with B to tau nu, it gets even worse. Now, I've got the good fortune that one of my friends was working on B to D tau nu and D star tau nu, so I got to ask him lots of questions about it. And many years ago we both worked on B to tau nu, so I've sort of got an inside view of what this really means. And so far I've not come across a model which explains this, so this is extremely exciting. So anyway, the CKM matrix is a very visual way of combining lots of different measurements that over-constrain this CP violating parameter that gives us more matter than antimatter. And it's something we've got to keep our eye on as LHCb, Atlas and CMS, as well as SuperBell, continue to get more and more constraints on this. And who knows, the next big discovery in particle physics could come out of the CKM matrix. As a bonus, we just want to give a shout out to another YouTube channel out there who's also doing an advent calendar this year. So if, like me, you're a fan of recreational mathematics, then you'll probably really like the Numberphile channel. So check out the link here and that will take you to the videos, and you can get new mathematical facts every day as well. See you tomorrow.